And first and most greatly, thank you, Brian Arthur, for joining us, even though online, but that doesn't slow down our happiness. It's an honor and privilege to host you, to chair this session. Brian, I've been raised as an economist and a geographer, and I remember in the 1990s reading your 1994 book on increasing returns and path dependence, which was really enlightening for me, also for building a bridge between economics and geography, understanding how regions evolve, how some of them take off and others wane, so to say. And I think I also like your statement. It's complexity economics is not just a niche or a heterodox corner of economics. It's just economics done in a more general way. So let's push that a bit more today. And I think it's not just economics done in a general way. It's also a meeting place for economics, meeting mathematics, computer science, history, geography, sociology. In a sense, it goes back to the political economy tradition a long time ago, which economics was founded. But of course, we're living in 2021, and we're living in the age of big data, in the age of networks, of interdependence, much more so than in the past. And I think also the most recent crises have learned that equilibrium states are perhaps more rare than we think, and that we should focus much more on processes, dynamics, events, phase transitions, and things like that. I think the bread and butter of complexity language, so to say. It's an honor and privilege to have you here. I think you're also very much in line with what the ambition is of the Complex Systems Center, bringing together people from all kinds of different social and natural sciences to better understand reality and perhaps even improve it. Having said that, I've put the bar very high. The floor is yours.
Oh, thank you very much indeed. I'm seeing at the moment that there are 5 people present. Are there any more than that I'm missing?
59. I think you have to scroll down.
Okay.
The small button on the right is 59 and more joining.
Gotcha. Oh, wow. Okay. Yeah. Okay, well, I'll go ahead and thank you very much for the introduction. I'm delighted to be here. I should tell you I'm speaking from South Africa, so I'm in the same time zone as you are, although it's late summer here, not spring, obviously. So what I want to talk about is foundations of complexity economics, meaning not nitty-gritty stuff, but rather giving a broad overview and trying to place it in some context. I know all of you looking at this are very likely experts in complex systems, so I won't talk too much about that. But what I want to talk about is how this works out in economics. I don't see this, by the way, as controversial, as a point of view that's taking over more and more, and I certainly welcome that. Anyway, let me kick off, and just as an overall context, see if I can get this to work, just a moment. So start with a very big picture that roughly from 1900 to the present, there's been, as I see it anyway, a constant shift in the science, or a pretty steady shift. So in the 1800s, science was deemed to be more about orders, what we would now call Newtonian. There's a lot of determinacy, there formalism, very logically based on standard mathematics. If it was behavioral, it was based on deductive logic. There was a fair amount of stasis or equilibrium, or whatever you want to call it, in science. Again, very much based upon Enlightenment thinking, and before that, the discoveries of Newton and others. Now, over the last 120 years, things have become much more organic in the sciences. I'm talking here about physics, physical chemistry, particularly biology, molecular biology, the whole gamut of sciences, even geology, ideas of contingency, small events pushing you down one path and not another. Indeterminacy, I should throw in unpredictability, reasoning that's based, or outcomes that are based on behavior, not on some form of deductive logic, and an embrace, instead of stasis or equilibrium, an embrace of evolution and openness, and very newly, very much a sense of process. I say this is from 1900, sounds very precise. It could be even more precise because it was 1 week before the new year of 1900, December 1899, that Max Planck launched the idea of the quantum. That was the weekend between Christmas and New Year. And that was a sort of kickoff. I think sciences have been shifting because they've widened their point of view. There's been a lot of emphasis on indeterminacy. We've had Gödel's theorem, we've had the foundations of mathematics look not that very well defined, etc., etc. Evolution is now fully accepted. And we're shifting to asking how things generate, how patterns are generated, or how indeed the planet has been generated, or whole galaxies are generated. We're shifting it much more into a process view. Part of that, I'm going to argue here, has to do with the coming of computation. We can start to compute things. Complexity, I don't need to tell people participating here, but I just want to point this out because there's an analogy in the economy. I see complex systems in general as having elements that react to the pattern those elements create. That changes the pattern. So cars form something you could call traffic. The local pattern of traffic around a car changes the car's, what the car does. So cars are reacting to traffic. Traffic's forming out of those reactions of the cars themselves. There's what I call a recursive loop. Other people have noticed that as well. Does that apply to the economy? Well, just to give the economy its full due, it's not anything simple. It's an enormous set of arrangements and actions and things being organized and changing. And the players in the economy and economics, we call those agents, as you know. They might be consumers or producers or banks or governments. They're reacting all the time to some set of outcomes they are together creating. It might be like cars and traffic, they're relating to the particular market, an oil market, say, that they are in, but they're reacting to the outcome they're creating. People tend to tell me that economists are applying ideas of complexity. Adam Smith noticed this and commented upon this 250 or so years ago. So it's not exactly new in economics that there is a recursive loop. The players in the economy create outcomes. Those outcomes, they react to. So it's a kind of mutual recursive loop that gets created. In the early days of economics, economists were well aware that this was, if not a complex system, that word wasn't used, but it was a very complicated system. And given the time, especially by the mid-1800s, there was an impetus to make this scientific, not just in words, but say in mathematics. In fact, in 1783, if I recall, not that I'm that old, but science was taken as needing to be mathematical. Kant that year said the criterion of true science lies in its relation to mathematics. He was dismissing chemistry, which couldn't easily be mathematized at the time, nor was it fully mathematized. So the whole idea was to sort of make things mathematical if you could. This happened in economics, but it was really fine-tuned by Paul Samuelson in the 1940s and by his followers at MIT and places like the University of Chicago. Economics became very mathematical, and the standard approach launched. It was in economics already, but it was very much refined by Paul Samuelson, made several assumptions to do this. One was that agents would be perfectly rational, logical, optimizers, facing well-defined problems. Fair enough. That to make everything simple, at least in our studies, we'd assume those agents are identical, or at least if they're not identical, there might be n classes of them, and all agents knew how other agents in those classes operated. And further, this is the common knowledge assumption that agents know other agents are identical, or they know all about them, and they know that other agents know that other agents know such things, etc. And finally, we're interested in outcomes that happen to be at equilibrium. So agents, each agent is showing behavior or employing behavior that produces an aggregate outcome that gives no incentive for that behavior to change. I want to emphasize that economists are certainly not idiots. I include myself in there, thank you very much. But economists are not adopting this to appear silly. These are taken in economics by theorists as being convenient assumptions. You have to simplify somewhere, and these appeared to be a reasonable set of simplifications. And I draw your attention to rational agents and equilibrium, and the idea that we know that everybody, in principle at least, is exactly like us. So given those assumptions, you could solve problem after problem in economics. Samuelson showed how, but there are many, many other people. I'd certainly include Arrow, Debreu, and many others who followed in this pattern of mathematizing economics. I'm a mathematician largely. I was a very good friend and protege of Ken Arrow, so I'm not on a campaign against them. Anyway, the result of all of this is what you'd call a beautiful structure. In economics, it's somewhat machine-like. It's like a machine humming along. Each part is fairly well resolved. The structure is elegant. When I entered economics as a grad student from mathematics, it appeared to me an incredibly elegant structure or set of structures. It had a lot of perfection in it, optimal this and optimal that, and social optimality, Pareto optimality, and it's extremely mathematical, very, very highly mathematical, although using mathematics that is largely linear algebra and calculus. I'll have more to say about that later, maybe in the questions, but note that it's highly mathematical. And in some way, at least in the mid-1980s, economists felt that they kind of had nailed a lot of what was necessary to nail in economics, and it was very well received an awful lot of prestige. Beautiful, elegant, ordered, rational, etc., etc. But I've put the but in large letters. But this equilibrium association, it puts this enormous filter on what you can see. I want to emphasize, if you look through different sorts of telescopes, if you look at, through an optical telescope or an X-ray telescope, say, at the sun, you see very, very different versions of the sun that looks completely different. And so if you have this equilibrium assumption, you can see some things very well indeed, and others not well enough. And there have been complaints. People like Joan Robinson, many top economists, from Schumpeter on down. Schumpeter didn't live to see this much of how economics came out later. But they complained that there wasn't any scope in this for structural adjustment. Yes, a parameter could change. There wasn't structure for exploration, for creation, for innovation, for any transitory phenomena. If everything is at equilibrium, it's static. History didn't matter because if you assume that equilibrium is unique, you're going to get there one way or the other. Time itself disappears. And among thinking economists, not just method people turning the crank, this is either regarded as slightly unsatisfactory or a true scandal. And many economists, first-rate ones, claim that this is all very fine, but it lacks reality and it lacks authenticity, and somehow it's dead. I remember my colleague, John Holland, Santa Fe, I asked him, John, what do you think about equilibrium? He says, anything at equilibrium, he says, is dead. So there's a lot of complaint that it lost its aliveness. That's the background for a meeting that we held at Santa Fe in 1987. The Institute was a startup. Nobody had ever heard of it. It was in the middle of nowhere. I remember Ken Arrow stopped me in the quad at Stanford and he said, do you want to come to a meeting in September? It's in the Rockies somewhere. I think it's in Santa Fe. So the Institute was only starting up. That meeting was organized by Arrow and Phil Anderson. Some of you are physicists, you would have heard of him, Nobel in condensed matter physics. And David Pines, a first-rate physicist also. And we met, and it was quite a stellar bunch. There were 10 people on each side, scientists and economists. Among the scientists were John Holland, many other people, Don Farmer, you may know, and others. Among the economists were, besides Arrow himself, Tom Sargent, Larry Summers, etc. So it was quite a group, and these people were exchanging ideas for about 10 days. I remember it was extraordinarily exciting, and but also exhausting. The meeting was a success, and the new institute had no research happening and decided after this that the first research program of the Santa Fe Institute would be held on the idea of the economy as an evolving complex system, to really figure out what that meant and see if we could have a serious go at it. Holland and myself were asked to direct the program. John couldn't make it, so I found myself on a sabbatical in 1988, running the very first program at the Santa Fe Institute. That's why they've working papers, not tech reports, because I was an economist. So this was Santa Fe's first program. And I remember after about a month of deliberations and head scratching, what should we do? What should we do? Finally, we weren't quite sure. Should we be doing chaos theory? So that was a big idea 23 years ago or so. Should we be doing this dynamics or that dynamics, or should we be looking at evolution in the economy? And I called up in desperation, finally phoned Ken Arrow. There was no email much at that stage. I said, Ken, what do you want us to do? Arrow called Anderson. Anderson called John Reed, the chairman of Citibank, who was funding us. And the word came back from Reed to Anderson to Arrow to me, do whatever you like, providing it is at the foundations of economics and providing it is non-conventional. And I remember holding the phone and Arrow saying, providing is not conventional. And I had an instant vision at the time. It's as if the Augustinians in wherever, Wittenberg in 1520, phoned up the Vatican and said, you know, we're trying to think about theology here. What do you want us to do? And the Pope says, oh, do whatever you like, providing it's foundational and not and hasn't been done before and is not conventional. Anyway, I couldn't believe our luck. So what we decided to do is just to ask the question, what if we looked at more reality and let the standard assumptions go? What on earth would we get? We did this, or I speak for myself, we took this over as a very high risk pursuit. And there was a kind of, what the hell, let's have a go at this. One thing we noticed straight away is that in any realistic situation, agents are not identical and they're not that well informed. If you look at Silicon Valley, where I normally operate, firms go into new markets all the time. The market might be, say, for autonomous trucking fleets or for some version of AI, but you might be a firm, you don't know how the technology is going to work out, you don't know what other players are going to do, you don't know what their strategies are going to be, you don't know what their resources are, you just don't know. And we realized quickly that that, of course, links up with a very standard idea in economics called fundamental uncertainty. Goes back to Frank Knight and to Keynes. Keynes explained this is that if you're looking at something in the future and the future is reasonably complicated, Keynes pointed out in his version of it, like, will there be a war, he said, writing in 1937, in 3 years' time. The most rigorous answer is you don't know. There's no way to put a probability or a set of probabilities on outcomes. It's just fundamental. You simply don't know. There's some things you might know. And so I realized, or we did realize, I should say, that this led to a sort of a weird syllogism. If you have fundamental uncertainty in some problem you're looking at or issue or situation in economics, if there is deep fundamental uncertainty, then decision problems are simply not well defined. There's no way to put probabilities on things. There's no way to say everybody's like me. There's no, you simply don't know enough about the situation or the other players or the future. And so the decision problem ceases to be well defined. If that's true, rationality that we go on and on and on about in economics isn't well defined either. Not well defined means there's no logical structure to structure the problem as a logical one. If it can't be structured logically, then rationality or rational logic isn't well defined. If that's the case, optimal behavior is not well defined. And this brings a gigantic oops. Standard approach gets stuck. And I remember we talked about this a long time, and Ken Arrow and others came out, and I said, Ken, do you believe that all problems are well defined? And we sort of presented him with a syllogism that kind of says, I believe you, he says, but I don't know. He says, what can you do? You either well-define problems and solve them in economic theory, or else what can you do? And we got stuck there. But on our team was an amazing person called John Holland. We brought John, joined us for some time in Santa Fe. And John had been pointing out that people do act in situations that aren't well defined, and they do this all the time. John didn't tell us this. This was actually, well, we quizzed him a lot on this, but John had spent a lot of his life as a mathematician and then a computer scientist. I believe the first PhD in the US in computer science from MIT, I think in the early on, like in the 50s. John had spent a lot of his life looking at situations that are not well defined and teaching automata or computers, or what we would now call artificial agents, to learn about these and figure out how the system might work, what might work, and so on. Not in a well-defined way, assuming there's a model and you're adjusting a parameter, but trying things. John's idea was that if you don't know, or if agents don't know, or machines, they try to make sense. Very often they form hypotheses. It could be this, on the other hand, it might be more like that. They try these hypotheses out and they keep adjusting, including throwing out their ideas, their hypotheses, and bringing in new ones. I'd recently been working at the time for Citibank in Hong Kong in the analytical division. I was leading a group investing in foreign exchange. I should have said I had been working for a bank in Asia Pacific. So scratch that previous reference. But I noticed that the players in the foreign exchange market, watching them operate at 3 in the morning, had a lot of hypotheses. Oh, the Bank of New Zealand's just come in, and the Chinese Central Bank has entered. Now that means, and so on. So we do live in a world where a great deal of the time we're in situations, not in well-defined problems, and these situations are not well-defined, and to cope with that, we're continually trying to make sense, form mental models, if you like, trying these out, tossing them aside if they don't work, generating new ideas and adjusting constantly. John had given a talk on this in that 1987 meeting that we'd had at Santa Fe. And I remember watching John talk. It was the afternoon of the first day. He had the whole afternoon. I sat there mesmerized at what he was saying. And it went through my head that John Holland, I remember thinking these explicit words, John Holland is the answer. All we needed to do in economics was to find the question. Turned out the question really was, how can you do economics or economic theory in situations that aren't well defined? John was telling us that we could build computer models that maybe had formed hypotheses. He'd written a book called Induction with other people, making sense, trying out things, and so on. So we had an idea upon which we could work. And if, as people did this, of course, the situation would change if they tried out hypotheses. And they'd have to rethink and readjust. It may converge to something or not. You don't know. So this meant that if we followed this sort of logic or these ideas, we would land in a world where forecasts, many individual forecasts of players, not optimal because you can't define optimality here, or strategies or actions were all kind of thrown in to the mix, and they were being tested for survival within a situation those forecasts or strategies or actions created. So in other words, behavior of these multiple agents in a given situation, we're creating a sort of an ecology of strategies or an ecology of forecasts. And individual agents were trying to cope with that and adapt to that and find their own way through that. Each strategy you could think of as a species. So notice one thing about this, the whole idea of evolution has emerged. It's not built in. If you start to think that way, that ideas or hypotheses that aren't very good don't last and they're replaced, you're immediately in an evolutionary world. So you get evolution, so to speak, for free. You get one other thing for free, and that is that you get what is now called agent-based modeling. We started to build models in Santa Fe where we were saying we will have agents, and those agents be trying out different strategies or different forecasts or actions or whatever you want in the context of other agents doing that. There was no name for this. We called it element-based modeling. But in 1991, John Holland and John Miller, both of Santa Fe, talked about this was agent modeling, and a convention arose to call this agent-based modeling. I am not saying that we invented that. I think there were predecessors, but certainly this became a lot of the basis for what we did. So I want to show you an example of this, and loosely speaking, I call this the stock market. To be more precise, you would call it, I don't know if you call it agent-based, it's certainly agent-based modeling, but it's a theory of how asset pricing works. Loosely speaking, I call it stock market. Bob Lucas had come up with, I thought, an ingenious and rather beautiful standard neoclassical model in 1979. And the way that worked was you have identical investors use some identical forecasting method to buy or sell stock. And if the stock pays off in some sort of random manner that's fed in, some earning stream that's random, how will prices be formed? So think of it this way. In Bob Lucas's world, all the investors are identical. They're all infinitely smart. They can all solve this problem in their head of buying or selling stock. And they all have a little plastic forecasting machine, an identical one, on their desks. And earnings take a bleep or a dip, and the forecasting machine tells them next time or next month or next week, the price should be worth such and such. Lucas's question was, what forecasting model would be in equilibrium? It's called rational expectations or rational forecasts. What forecasting model would, on average, give you, on average, correct forecasts? Mathematically, the solution was gorgeous. Neoclassical economics, beautifully done, 1979, gorgeous solution, but a few embarrassments to it. No trading takes place in this world, zero trades. There are no periods of activity and inactivity that you see in real markets. There's no market psychology. Everybody's the same. They all think the same. There's no technical trading going on past prices, and no bubbles, no crashes. Everything's rational, perfect, and the price is adjusting to the earnings all the time. You might be puzzled, why is there no trading? Well, all the agents are identical. So if one agent wants to sell, they all want to sell. So there's nobody to buy. I mean, this is slightly embarrassing because there's a huge amount of trading volume in a real market. But if they're all identical, they either all want to buy, all want to sell, and some little demon inside the system just adjusts the price so that people are indifferent between buying and selling, and that's how the price adjusts. Anyway, real markets show periods of very high volatility and then periods of not much. Market psychology, bubbles, crashes, and plenty of trading and so on. So we determined that John Holland, myself, Blake LeBaron, Richard Palmer, and Paul Taylor, Taylor was from City of London Finance, Blake LeBaron's a finance economist, Richard Palmer is a physicist, and John Holland is the legendary John. And we decided that we would construct an artificial stock market, what you would now call an agent-based model. We decided this in 1988, got it going about a year later. What we would do is to replace Bob Lucas's identical investors, perfectly rational ones. We would allow artificial investors, little computer programs that could learn and change and recognize patterns, and but differ. And no investor, no artificial investor would be well informed at all or know much about other investors. All they could do is look at price and other indicators. And each of these investors, whoops, just a moment, I can go back one. Each of these investors uses their own rules. They cook up their own little machine, if you like. In fact, they might have 10 or 12 or a dozen or 20 predicting machines. And these are like different hypotheses of how the market's operating. And they follow the ones that have recently been most accurate. So basically, we haven't, there's no rational, if you don't know how other investors think and they're not like you, there's no rational solution. So we're cooking up a lot of automatic investors that will probe the market and try to discover what operates well. But then doing that will cause the market to change. So they'll have to generate new ideas. What did we find? One of the commentators in what we were doing was Tom Sargent, really, really smart economist, later to win an economics Nobel. And Tom said, it'll work out, it'll converge to rational expectations. I wasn't so sure. John wasn't so sure, but he just said it'll converge to the Lucas solution. So what we did in this diagram was we plotted the Bob Lucas solution. We figured that out, plotted that. I'm pointing to it, but you can't see. We plotted that, maybe I can point to it here, on the top graph. And then we allowed our artificial agent, now called agent-based system, to operate and prices to come from there. And Richard Palmer came back and told me, we can't find statistically any significant difference. And I was really disappointed. It meant that Tom Sargent was correct. I'm not against Tom's a really fine person, but it was kind of an argument that we'd had. We couldn't see any difference really. And statistically, differences were maybe detectable, but hang on. And then I noticed something. I noticed that places like here, the artificial agents had a little crash. In fact, if you notice other places, there's not much change here, but there's quite a big run-up happening. And there's a minor, other minor bubbles and crashes. In other words, what we saw and begin to see was that we started to see the real market phenomena. If I can't get the slide back here. No. Bubbles and crashes, technical trading, and so on. So it was, this was very early on, like 1988, 89. We published something in the early 90s. And what my claim is that we were seeing real phenomena that come out when you build a fairly simple artificial agent-based model of the market, where our little agents had to learn what might work and relearn as their behavior changed the market. To put this, I've already said this, but the market hovered around the rational expectations solution. And in that sense, Sargent was quite right. But then we noticed that if we allowed how fast our little agents could react to go up a bit, then all these phenomena, real market psychology, technical trading using past prices emerged, periods of very high volatility and low volatility emerged, bubbles and crashes appeared and all that sort of thing. In fact, Paul, I was back at Stanford at the time, and Paul Taylor used to call me, and I said, Paul, what's the market doing? Meaning the one that we were, that we had operating on at the time, I think on a Next machine, or originally on my Mac Plus computer. And Paul was saying, you wouldn't believe it's somehow taken off. Things have gone a bit crazy, and then the next day it might arbitrarily settle down again. I don't want to explain how each of these phenomena emerge, but what I want to point out is that if you start a market at the rational solution, you wouldn't want to deviate from that. If everybody else is being rational, you would lose money. However, we're not in that situation. We're in a situation of agents working with or discovering behavior that works temporarily in the context of other agents discovering behavior that works temporarily. Notice there's no reference to rationality here. Nobody's being stupid, but rationality is not well defined. So this isn't some departure from rationality where you might lose, because nobody knows. Therefore, rationality is not well defined, and therefore everybody's trying to do their best to discover what works in an atmosphere of everybody doing their best to discover what works. And this is strange. If you're well-trained in economics, you'll find that difficult to accept, if not to comprehend. But basically, everybody's working in a situation in the context of everybody else working. And that just means that you're doing your best. But because you don't know what best is, and that's not well defined, it's not a departure from rationality. If that's hard to explain, or if I haven't explained it very well, let me give you one of my definitions of complexity. I remember somebody putting up their hand in a public lecture, and they were in their 50s or so. Professor, how would you define complexity? and I said, have you ever had teenage children? If you have, you know that there's no optimal solution. You're trying to figure out what's going on. They're reacting, you're reacting. You're doing your best. And it may all work out to the good, but there's no optimal rational behavior. You simply don't know what on earth is going to happen next. So I'm giving you this as a kind of parable. It's not extreme. And I want to just throw in a couple of remarks here. What I've been describing so far is a way of looking at the economy, accepting that we may not want to bring in the very restrictive assumptions. All agents are rational, all problems are well-defined, all agents are identical, and everything happens in some behavioral equilibrium. And I want to, what if you were to allow that agents aren't identical, and in reality, they don't know that much about other agents or the problem itself? Well, you're in a situation of mutual exploration, and you're adapting to the explorations of other people. I want to make two remarks about this. I'll skip ahead a slide here. And whoops. Yeah, let me go backwards here. There's this thinking, and I think Eric mentioned this at the start, connects with thinking of earlier economists, Thorsten Veblen, who wanted to see some evolutionary approaches to economics. In, I think, 1898, wrote a beautiful paper, or sometime close to that. Schumpeter himself, who admired the mathematical approach to economics, but never quite adhered to it. He got very tired of the equilibrium approach that he'd written a book about around 1906, and by the time he wrote his book on economic development, he had gone past that and was looking at systems that were unfolding, and the whole idea of entrepreneurs is a word that he largely introduced, creating the economy and adjusting and adapting to that. George Shackle, Liverpool, more recently, talking about the role of imagination. Where do these ideas come from? Where do these hypotheses come from? Hayek himself, who the University of Chicago didn't quite allow to teach when he joined them, but is now a pillar of the right. Hayek asking, how do you deal when you don't have perfect information? How would you run a whole economy where you really don't know quite what's going on? So there are ideas of evolution, ideas floating around. And to go back a slide or two, I came to realize that there are two very large problems in the economy, or you can classify problems into two types. You could have allocation problems, where you get general equilibrium or standard game theory or international trade, how much of something is produced and how is that in balance or the equilibrium. Other problems having to do with formation. Where do institutions come from? How do they arise? How do they form? Where does structural change happen? How do whole industries change their structure? Where does innovation come from? How does economic development work? These are all questions of openness and response to openness, and agents reacting to a situation that those agents themselves are creating. Those problems can't be easily mathematized, but you can put them on the computer carefully and watch formation happening. So I would say standard mathematics is very good at looking at equilibrium, balance, and allocation, not good at looking at formation questions, but computation in general is. And so given that complexity is about the formation of structures, then the sort of economics can deal with the formation of structures and do that rigorously. If not in standard mathematics, then certainly computationally. Let me go back one more slide. I've got these things a bit mixed up. I want to make, I'm coming towards the end here, and I want to make an observation about where does complexity economics fit with agent-based computational economics? The latter has been championed by Litis Fatsion and others, others that are good friends of mine. How does complexity economics, at least as I'm describing it, fit with ABC, agent-based computational approaches, which are pretty largely agent-based modeling? My response here, and it's in the paper that I'm basing this talk on, is that computation arrived, serious computation in economics, around 1980. We all got desktop workstations. We had computers, and computers were inevitable to come into economics. So my response to this question is that if you ask, how would economic theory adjust to the idea of computation being available, what sort of theoretical framework would you get? Yeah, you would get something like I've just described, complexity economics or some variant. But I think that more than anything, the ability to compute answers to such modeling would have been around in principle if we'd had computers 100 years before, but we didn't. So this came in the 1980s. If you think theoretically about that, you get a theoretical framework that in 1999, I gave the label complexity economics to that. It could have been called non-equilibrium economics or any other label. If you think in terms of what solution method the idea of computation gives you, you'd come up with something like agent-based computational economics. They're not that different. Complexity economics thinks in terms of an economic framework. Agent-based modeling thinks in terms of solutions and methods. Litis Fatsion and I finally agree that these are two sides of the same coin, and I wish the agent-based people well, and I think they refer back to complexity economics as well. Let me finish largely here by pointing out that, just to summarize here, what are the key differences? Well, neoclassical economics has agents that are very often or largely identical, or at least fall into a small number of classes that people know about. Problems in in complexity economics, agents are realistically diverse in approaches, in possibilities, and even in intelligence. In neoclassical economics, problems are well defined. In complexity economics, they need not be well defined. In fact, it might be more of a situation than a problem and ill-defined. Agents are rational, they're hyper-rational in standard economics. In complexity economics, they may face fundamental uncertainty. Explore makes sense. The metaphor in the neoclassical case is roughly a machine. In complexity economics, the metaphor is much more an ecology, something that co-evolves out of strategies or actions. Static equilibriums assumed in most neoclassical studies. It's not assumed, it may emerge in complexity economics. Perpetual novelty may emerge. Standard mathematics is used in most of neoclassical economics, but computation is also used in the complexity studies. These are not hard and fast. If you're a pretty good economist, you might say, well, I know a complexity economics study that has equilibrium as an assumption. Fair enough. But what I do want to point out to you is this. I'm asked from time to time, oh, complexity economics, isn't that an extension of neoclassical economics? It's kind of add-on or a bolt-on. And my response is no. In all those things down the right-hand side, as a special case, you could get identical agents as a special case, well-defined problems as a special case of ill-defined ones, etc., etc. And so I'll use a phrase that Dave Collender, a good friend of mine again, points out. He said, complexity economics, and pardon me for being rather a reach. He said, that's the new general theory. It's not a bolt-on, it's not an add-on. It actually generalizes the tenets or the assumptions of neoclassical economics. Fair enough. I'll finish. I mentioned Dave Collender a moment ago. He's a wonderful thinker in economics. Collender came up with this, I don't know what you would call it, an allegory. He imagines that the year is 1870 or so, and economists are all gathered at the base of two mountains. They're very high mountains, higher than the ones I'm showing you, and they're in the clouds. And they're trying to figure out which mountain they should climb, but they can't see which one's higher and which one's harder and more challenging or more interesting. So they climb the mountain that they already have a pathway to. And that's, as Collender puts it, the mountain of well-definedness and of order. Or you could put it, the more Newtonian mountain. And they have all the gear and all the equipment. They climb that mountain over the next 100 or more years. And they get to the top of it. And at the top of it, they're out of the clouds. And they can see the other mountain. And they say, oh my God, this other mountain's higher. And more interesting, that's the mountain, as Collender puts it, of ill-definedness, of organicism, of one thing building out of another and onto another. And they start to say, oh my God, we're happy we've climbed this mountain of order, but my God, we should have tried this other thing all along. My comment is that we're starting to climb that second mountain. And I don't think this is strange, weird, or anything. It's just where economics is heading and where science is heading in general. Thank you.
Thank you. A little applause virtually. I'm sure there will be many questions, and I think I have to moderate that. We're not going to climb mountains because we're just staring at our monitor, but we've also been listening to a fascinating story on the history and perhaps also the future of complexity economics. Who can I give the floor?
Eric?
Emmy Vochtlander, please, could you ask your question?
So first, Brian, thank you so much for the great talk. Yeah, I've been wondering myself. I think complexity economics or complexity thinking is really critical for us to realize long-term growth. Actually, I posed this question before, but it's still a hard question for me to answer. So what aspects do you think are most fundamental in hampering us to realize long-term growth? And why do you think it's so hard for people to change their assumptions? So some of the assumptions that people have is that gradual growth is really good, or that that we should be looking for the optimal solution, for example, for climate change. Or actually, you see it on the stock market a lot, that predictability is equated with quality, meaning predictable outcomes generally means a higher share prices. So why do you think it's so hard to really change people's minds around this?
Well, you really asked, if I understand it right, you asked two different questions. One is, what can you say about long-term growth? The other is, how do you change people's minds? I start with the latter one. I wish I knew. I remember in discussions in Santa Fe, I remember somebody remarked that people who were, this is a long time ago, like 30 years ago, or 25 years ago, people who were over 65 immediately got what we were trying to say in complexity. People under that didn't get it. And Ken Arrow, theorist, was in the audience. Arrow says, why? Why is that? And I said, because you trained them, Ken, which was a sort of cheeky answer. But people have been trained into seeing economics as operating under a standard set of assumptions, the ones I outlined anywhere, and that's taken as given. People tend not to question the assumptions, but they tend to spend a lot of time generating solutions, but without looking at assumptions. So I think that economists, by and large, are extremely bright. I'm not objecting to that, but like any other discipline, they've been trained in certain approaches, certain methods, and they know how those work. There's a new generation of economists coming along that are comfortable with models, with algorithms, with agent-based modeling, and this will change, but it's taking some time. Another quick thing I'd like to point out about that is it was Rob Axtell from George Mason pointed out to us one time that game theory took 40 to 50 years to get hold of economics properly, to be fully accepted. And in fact, von Neumann had predicted it would take 40 to 50 years. And he was right on the money. Behavioral economics similarly took 40 to 50 years, started in the 1960s. Now those are considered non-threatening and so on. If the good news is that complexity economics would only have another 10 or 15 years to go before it becomes central. Bad news, at least for me, is I may not live to see it, but that's okay too. To go back to growth, it's a really good question. Let me put up a slide here just to answer you, at least that's my excuse. Hang on, let's see if I can. Yeah, whoop, I'm not getting this to work. Just a sec. Yeah, and I'll try and make this a fairly short answer, but I want to point this out, and that's the subject of this other paper that I included. If you do standard equation-based mathematics, this is the way I was trained anyway, more a mathematician than anything. If theory is based on algebraic or calculus or algebra, or linear algebra type of mathematics, equation-based, then it's restricted only to nouns. And so actions are not, actions and processes are not included in that. You have to have all kinds of elaborate workarounds. And so verbs are not included, but computational approaches, algorithmic mathematics allows actions, processes. If this process has happened, then initiate that process and so on. So we can model those using computation. Now it happens that economic growth has been defined originally by Bob Solow, 1987, 88. There's plenty of people thinking about growth before that, but he thought seriously, you know, the first one of the early growth models that's been taken up by Paul Romer and others. But they're defined in terms of nouns. You have this much labor, you have this much capital, that gives you this much GDP or this much output. What they didn't ask in this noun-based mathematical setup was, is there anything else? You know, Solow famously pointed out that 80% of GDP growth can't be explained by capital or changes in labor and capital, which is whopping. That's 4/5 of economic growth. We don't know. It's kind of dark matter. Conjectured that it was technology. I'm sure he's quite right. But you can't get a theory of technology easily. I wrote a book called The Nature of Technology. So I have a book on that that's been scrutinized. But more than anything else, if you say economic growth depends 80% on some weird thing called technology, where does technology come from? Well, it comes from a process. And the process is called invention and innovation, but those themselves are processes. So if you don't think in process terms, you're not going to understand much about innovation. You're kind of saying, well, a little bit more of this will bring you a bit more of that. My reaction is, give me a break. You know, that's not how engineering works. It's not how real invention works. Invention works by combining certain parts, and you create something new. Like a laser printer is basically a combination of computer processor, a laser, and a Xerox drum. And you can churn out copies that way. So what I'm saying is that it seems to be wandering my answer to, but really good questions. What I'm saying is that if you don't think in process terms, which equation-based mathematics doesn't encourage you to do, then you can't understand where an economy comes from really, how growth happens, how economic development happens, and for that matter, how cities grow. They grow organically, not according to some equation. And these things are all related by events. So to go back to the slide I'm showing you now, economics is equation-based. Old-fashioned physics was, less so nowadays. Biology isn't. Why is that? Well, because biology is basically a well-understood collection of processes. How DNA replicates, how it splits, how cells split and divide, how things how the processes that constitute embryology or speciation, you can't put them in mathematics because these are not quantifiable nouns. So, pardon me for this hobby horse, but it's the subject of the paper that I circulated.
Yeah, and it's very clear. Thank you. Yeah.
Okay.
In the context of economic growth, learning is something different than achieving optimal or perfect knowledge, for sure. Yeah. We have two questions in line. Deb Panja and Anne van Brugge. Deb, please ask your question.
Yes, well, thank you for really very inspiring talk. So you mentioned about the reactive and gave this example for the drivers reacting on the road. And this kind of feedback mechanism is of course very biologists see that all the time. That at the mesoscale level, so if you think of a biological entity at a mesoscale level, it sees its environment and according to that it reacts. So it's similar to the drivers and the road. And I guess if I understand your talk well, then thinking wise, you are basically taking it one step further, because if I'm an agent who's wanting to invest, then I would want to see what my chances of return are. So I kind of project myself or how I see other people to be to behave in future, and then I want to. It's like a reactive. So I would react to something that is presumably going to happen in the future. So you're also joining not just the reactive element, what is happening here and now, but also from the future. So not just the space of agents, but also time. And probably that makes the problem, I mean, not probably, but that makes the problem far more complex. Do I understand that correctly from your talk?
Yes, I think so, absolutely. I would say this, that there's an idea that physics is hard science and economics is soft science. This is not at all true. If you have a physical question, a physical problem, you might have an ion in a lattice in physics, and that ion can flip. I don't want to be technical here anyway, this isn't my specialty, but the ion can flip to be up or down or spin this way or that way. You've got some spin thing happening. But ions are only reacting to neighboring ions, whereas agents in the economy, the players in the economy, are not just reacting to the position of other agents, they have to react to what they think other agents might do. So I would say that economics is a high complexity science. Physics, and I don't want to be mean or controversial, in that sense is a more simple science. Atoms or planets are just reacting to the situation of other atoms or planets as they are, modulo time, of course.
But physics has equations and economics doesn't.
Au contraire, economics is equationed up to here by now. Physics has equations, and I think economics borrowed this habit from physics. I'm not against that. But what physics is discovering is that if you're looking at condensed matter physics or you're looking at modern physics, you're looking at a lot of elements that are flipping around and changing their behavior based upon where they are. You can't always do that. Some of you might know about self-organized criticality, the physics of sand piles by Back. You can't mathematize that easily, but you can look at that as a computer algorithm. And so certain things are not easy to mathematize. and shouldn't be mathematized in equations, but they can be put into algorithmic form. We can study them on a computer. Economics took on the mathematical program, and it's worked okay. But I think if you want to look at things adjusting to other things properly, and agents being properly not well informed and not being perfect and so on, you don't quite know how things are going to coordinate, and you can play it out on your computer. So it's kind of a bit like saying, if that appears a bit absurd and unreasonable, say, what if I wrote a story where all the characters in my play show up on the stage at first, and they all know how all the other characters are going to react, and they know the other characters are the same, and so on. So they all know, and everything's in equilibrium. It's not much of a play. The play gets interesting if the characters are reacting to a situation, they're trying to get ahead of the situation, but that causes other characters to react and to change their ideas, and maybe if it's Shakespearean, even to change in their very character. Then things get interesting. So this is the change we're talking about. It's making the stories in economics can be studied on the computer more easily, that sort of story. Hard to do certain things in mathematics, but I'm not against mathematics. I keep saying that's what I was trained in.
Okay, thank you.
Thank you, Brian. Your response reminds me of the statement by Albert Einstein choosing physics because economics was too complex for him. But well, that's a little piece of history of science. Anna van Brugge, please pose your question.
Thank you so much. Yeah, so I'm wondering, I'm curious, I work at the National Institute of Public Health and the Environment, and we're also now looking like what is indeed this potential of agent-based modeling, not just for economics, but we're actually looking at something called circular economy then also, like how, and I wonder, this is, I'm curious, my question is twofold, like on the one hand, like what could be also the potential of like agent-based modeling and maybe bringing together something that is more like also the physical processes that are involved with an economy that maybe we've now kind of divorced from it and we look only at like the monetary flow or so, and what could be the potential if we apply agent-based modeling also to the physical part and the materials of our economy. And then the other question is like, if we then use these kind of models, how do we ensure that they also really lead to insight for maybe like policymakers or those building the model? Because I think sometimes like we get so involved with building a technical or a theoretical model and we forget kind of the social process that's around it for it to really lead to insight. So I'm curious, what are your thoughts on these two aspects of agent-based models?
The first aspect again was what?
If like to look at something like circular economy, like the material flows of our economy with agent-based.
Yeah, well, it sounds like you're very much, working in government or working in some area where you're interested in applying economics. My advice would be that agent-based modeling is here, or computational modeling is here, and it's probably worth getting into simply because it's promising, it delivers certain things, and it's worth investing in so that your department or your group or maybe yourself knows how to do that. And certainly that's my own attitude to it, that, you may as well learn it if you want to be up with the latest methods. Is it worth doing, or how should you do it, I think is the other question you're asking. I would not want to tell people to try to simulate a certain situation, and just look at that alone. I think the value of agent-based modeling or computational modeling is that you can do computer experiments. So typically in the science, you have theoretical methods and you can work out the implications of that, maybe using mathematics, or you have a lab and you can watch physical things happen in your lab. But now we have a third branch of science. Some people pointed out, and I agree with it, a computational lab, and you can take your problem and strip it down a bit, make an agent-based experiment out of that, a computational one, and then you can see how would it work if you change this assumption or that assumption, or these parameters or that parameter. John Holland used to talk about flight simulators for the mind, and I think that that's a nice way to look at it. You're not saying this has to happen, you're not saying that has to happen, but just as if you do mathematics on a problem, you get great logical insight into how that problem operates. And if you change this or that parameter or assumption or add a variable, how would it readjust? In computation, what you can do is run the experiment, make sure it's working, and then you can do all sorts of variations. So we're getting away to be more precise about it. In engineering, we're not looking so much at systems, say like the electricity grid, that are optimal. We're interested much more in engineering and in industry, in systems that are robust or resilient. They're not quite the same thing. We're looking at what if we throw the perfect storm at the grid, how would the grid readapt or readjust? So you're not just looking at optimal behavior, but with that sort of modeling, you can certainly look at questions of how should the system adapt, how will it adapt, what if half of the resources are missing, what would happen? And that's good if you're looking at supply chains or you're looking at economic growth or looking at planning in general. It gives you a much rounder view of the entire system than simply assuming it's defined by one set of assumptions that will never change.
Yeah, maybe because maybe there's not time to answer, but I really wonder like how to make sure that this understanding is not just with the modelers, but how is then this understanding, how does it translate to like everyone else that's maybe doesn't get to actually build the model, which I think with agent-based models is a bit more complex maybe. But okay, it's no.
You know, that's an age-old question in consulting and in any form of policy advice, but the only thing I can throw in there is to bring the policymakers on board and construct something that they can play with. Just to make this a bit more vivid, it seems to me that policymakers and most governments don't understand exponential growth. And so they, in the whole COVID situation, they haven't shown much imagination at all. And so they tend to think, oh, growth, sorry, we have it all under control with things locked down. We can sort of walk away, open up businesses, open up this, that, and the other. But if they had a flight simulator in front of them, they'd see very quickly if they relaxed things too far, then exponential growth will take off, just as it has in India, and they'll be in big trouble again. So I do believe that we can help policymakers thinking, and we can show them things on a screen. And I've benefited a lot from that over the years. Put it on a screen, watch things work out, etc. And certainly in COVID, that would have saved hundreds of thousands or even millions of lives if people had had a much better idea of exponential growth. We had this thing, lock it all down, then walk away and open it all up. You know, you lock it down, you want to keep it locked down until it disappears further. And it's like, you have a fire, a forest fire, say in a remote place, you put it out, you walk away, but it's still smoldering. And you walk away and you're gone for 3 days and you come back and say, oh my God, this thing's blazing again. So having very good visual versions of that, I think, is so that you can look at that, get a feel for it, get an intuition for it. Yeah, that needs to be well done. That's an art. It's not a science, but it's very, very useful. That's the whole way you train astronauts, or you train pilots and so on. You put them into situations they haven't seen, and so they have a much wider sense of how things operate. Computation can help. I'm not saying computation is the only thing. I still like mathematics. What we need to do is understand that we have a new method or set of methods. The computer is changing every science, and economics is one of them. Complexity economics comes out of that change. So does agent-based modeling, and so does policy analysis change.
Thank you. So visualization as a bridge between science and policy is an interesting insight here. We have more than a handful of questions, but I'd like to prioritize one final question for you, Brian, which is from Emil Robben, who asked, you have been in the field of economics for a long time. Where do you think economics is going during the next decades? What kind of implications would this have for society? For example, climate crisis and stock market crashes.
Who asked the question?
Emil Robben.
Sorry. Oh, you did. Okay. I'll just say this. Very short answers. I don't know. I wish I did know. But to put it in more of a context, economics changes every time new methods come along. So economics was very discursive in the 1850s, 1860s, and dealt a lot with reality. People in those days, like Alfred Marshall, a bit later in the 1800s, he went down coal mines, he talked to trade union representatives, he was interested in business and so on. When mathematics came along, particularly in the post-war era, people thought that they could axiomatize economics. Gerard Debreu thought that. So as these different methods come along, gathering of statistics, thinking about GDP, because you can get the statistics, all that sort of thing. Economics itself shifts and changes. The big thing that's come along in the in the last 30 years is the ability to do computation, to visualize things, and to have a sort of, to begin to model what people do in situations that are not super well defined, and where you can look at realistic outcomes. So behavioral economics comes along when you have the new method of being able to ask people, what would you really do? And ask them that rigorously and analyze that rigorously. Complexity economics comes along when you can start to model situations that are changing and people are adapting. So I would hope that economics starts to become more realistic than it's been. I would hope that it takes seriously that problems in general are not well defined. We know a lot about things. We know a lot about climate change, but we're not sure how this, that, and the other will work. As opposed to what? 1990, the Soviet Union and Eastern Europe, but the Soviet Union in particular, adopted a free market economy. And it didn't go very well because economists could plot out what a new equilibrium might be, but they weren't aware of the adjustment process of a system that had been almost, 70 years or more, running under socialist planning or communism. And what I'm hoping is that economics can be more realistic and can think about including theory, history, and think about including behavioral thought, which it is doing, and bringing more reality and less pushing the economy into a very tight machine that was required by the post-war mathematization of economics. Not sure how to put this. I did know Gérard Debreu, lovely man, and many of the protagonists who mathematized economics. But nah, I think I'd like to see a movement towards realism, much more emphasis on reality, real behavior, and I think we're starting to get that, and being able to analyze that rigorously. What about Austrian economics? That has everything to do with process, and it's not hung up on rationality and so on. Yeah, I'd like to see more of that come back. So I'm not saying anything goes. I'm just saying an engagement, more of an engagement with reality and getting away from hyper-formalized approaches, and certainly getting away from any notion that if you can do mathematics, that makes you somehow a superior being. No, let's go for reality. Rigor, in my opinion, my definition of rigor is really respecting reality and then deducing what follows from that, not setting up assumptions that will make your analytical machine work easily and convenient.
Thank you. Thanks a lot for taking us through the history and current state of affairs of complexity economics and even the future of economics, which could be more realistic with maintaining its rigor. Thanks again, Brian. Thank you very much for your enriching insights. We'd love to see you back at our center, perhaps even in real life in Utrecht, talking about reality, but we were very happy to have you here online via Stellenbosch. Thank you.
If I may say a word, just thank you very much. And it's an absolute delight to talk to a sophisticated audience that gets complexity, wonderful questions, and thank you for inviting me.
Thank you, Brian.
Thank you, Brian.
Okay.